hate percent weight volume. This comes up a lot though, sometimes in biochemistry when you're making like a 1% agarose gel. And so what it means is 1 gram of something per 100 milliliters. So if I wanted to make a 1% agarose gel, I would do 1 gram of agarose in 100 milliliters of buffer. And if I wanted to make a 10% APS solution, I would do 1 gram of 10 grams of APS per 100 milliliters, but normally I make 10 mils at a time, so I do 1 gram per 10 milliliters. So basically, percent weight volume means grams per 100 milliliters. And for the longest time, I'm like, where the heck does this come from? And let's put aside for a second the fact that you're dividing 2 different units, so like grams, so a weight measurement and a volume measurement. And you're calling that a percentage? So where does this come from? How do we get this percentage? So what it comes down to is basically the density of water. So water has a density of about a gram per milliliter. So this means if you take a milliliter of water, it's going to weigh a gram. And we deal a lot with aqueous solutions, so water-based solutions, in biochemistry and biology. And so the basic idea with this whole weight volume thing is like, so let's say if you add just like a drop of water to a pool, that's not really going to change. Or if you add the drop, like not a water, because that's the same thing. If you added a grain of salt to a pool, that's not really going to change the pool's density, right? So we don't need to worry about what we're putting in. We'll just say that if we put a little bit of something in, we're not really changing the density. And so if you kind of assume that everything just still has the same density, then it's like, okay, so now we have, if we put in like 1 gram of salt into our 100 milliliter pool, yeah, it's a really, really tiny pool, but we'll call that a percent. And so the reason why it's 100 is because it's a percent, and percent is 100. So that's why it's grams per 100 milliliters. The biggest problem for me is that the information it's telling you is kind of like irrelevant at the molecular level, as opposed to measures like molarity, which we talk about, which is moles per liter. Instead of molecules, let's think about cookies for a second. So we're making cookies, and so we have our cookie batter, and we're going to add some ingredients in the cookie batter. So if we go with percent weight volume, so say we have 100 milliliters of cookie dough batter, we're going to have 100 milliliters of cookie dough. And we want to have a 10% of the thing that we're adding. We want it to be like a 10% cookie solution, dough solution, or whatever. So we want to add 10 grams of something to our 100 mils, for our 100 mils of batter. So we can add 10 grams of chocolate chips. That probably wouldn't be very many chocolate chips. I have no idea how much a chocolate chip weighs, but we're going to talk in relative terms. So now if you wanted to add 10 gram, what if you added 10 grams of sprinkles? You'd have way more sprinkles than you would have chocolate chips. So, but we would call both of these a 10%, like 10%. So it would be like 10% chocolate chips or 10% sprinkles. But if you were to bite into that cookie, it would be way more sprinkly than it would be chocolate chippy if you were to like compare. And so the same thing comes up in biochemistry, but here the consequences are really even more important, because if you think about molecules reacting, it has tons to do with their concentration. So like how likely are you, if you were a molecule and you were swimming around in a sea, how likely would you be to bump into one of the molecules that we're talking about? And if we're using this percent weight volume, it doesn't really tell us anything about that, because just like a gram, just like 10 grams of sprinkles is going to be different amount of sprinkles than 10 grams of chocolate chips, and just like 10 or like a pound, you know, the whole like joke or mind teaser or whatever, where it's like which weighs more, a pound of feathers or a pound of bricks. Well, obviously they weigh the same, but because their densities are so different, you'd have way more feathers than you would have bricks to get to that same amount. And so then if you were to stick that into water and say, okay, we have a something percent solution or whatever, it would be the same percent, but you'd have like so many more feathers than you would have bricks. And so if you were swimming around in that pool, you'd find way more feathers than bricks. And so if you were a molecule and you were floating around and you had the solute, so the thing that you dissolved, had a higher molecular weight, so how much like a piece of it weighs, kind of, and it's actually how much a mole of it weighs, because if you were to measure a single molecule, that'd be so tiny. So we talk about it in moles. 6.023 times 6.02 times 10 to the 23. So it's a ton of stuff, and it's kind of like a dozen, where it's like just like a chunk that means like a certain amount. And so we can say we have a mole of this or a mole of that or a mole of that, and that just means 6 times 10 to the 23rd of that thing. And so it helps us deal with really big numbers without having to write really big numbers. So molarity is really helpful because you're talking about in terms of molecules. Value that is called the formulated weight or the molecular weight. So you can see for ammonium persulfate that molecular weight is 228.20 grams per mole. And if I were to look at tris base, the molecular weight is 121.14 grams per mole. So you can see that molecules can have vastly different molecular weights, just like a feather and a brick would have different densities. And so the molecular weight is kind of like that, except we're not talking about like per volume, we're talking about per molecule. And by the pure molecule matters is because that's what really matters at the molecular level, like whether things are happening. It's happening because molecules are interacting. And so in addition to like that cookie example, so a more serious example is like if you're making a solution and you want to make like a solution of tris. So tris is a buffer, so a pH stabilizer, so it can give and take protons to keep pH stable, because pH is a measure of the level of protons, the concentration of protons. So you go to make a tris solution. So if you were to make a percent weight volume solution, it would matter super duper greatly whether you started with tris base or the tris hydrochloride, so that the acid form, because these have different formula weights. So normally when you're making a buffer, you can like either start with one or the other, or depending on pH or whatever, but you're going to adjust the pH later. So you're going to add like HCl. So even if you start with the base, you're going to be adding acid to try to get it to the pH that you want to stabilize at. And so the actual thing that's concentration you care about is that tris part, so without the H. But you can start with either. And the reason why is because what we're doing is we're measuring in molarity. So that's talking about moles. So like how many of these individual ones. And so if we look at the molecular weight, we can see that for the tris hydrochloride, it's 157.6 grams per mole. Whereas for the tris base, it's 121.14 because it doesn't have that HCl. So this is you're going to need to add less of this to get the same amount of tris as you would for this if you were to go by grams. And so if you were to do it by like weight percent, you would have a different amount of tris, right? So we don't really use weight percent if we're trying to make any solutions or anything like that in that sense. But you will see weight percent come up a lot because it's kind of like convenient, and especially in like medical context. For example, like normal saline is 0.9% weight volume. But hopefully and remember the reason why that is because that's grams per 100 milliliters. You have grams per 100 milliliters, and the reason why you have that is because that would be, if you had like 100% water, it would be 100 grams per 100 milliliters, because it would weigh 100 grams because water has a density of about 1 grams per mil. And so it just happens to be really convenient. And since most solutions that we're talking about are water-based, especially like in medicine, then you can talk about like having a percent weight volume. The problem kind of breaks down if you go to anything that's not really dilute. So you could end up, so if you had 100% solution of something, that would basically be all of the thing would be your solution. But that would be assuming that the thing that that would be your solute, so this thing that's dissolved. But that would be assuming that like everything, that it had the same density as the water. So if you had 100% solution, you would have 100 grams per water, whatever. What if you had more than 100 grams of something into water? Then you would have like greater than 100%. So you can see it kind of breaks down when you get to bigger thing. But it gets super, super duper frustrating in like biochemistry and things when you're trying to think about more precise terms. But yes, it is helpful to know that you just put a gram of agarose into 100 milliliters of buffer to make your agarose gel. But yeah, so let's look a little bit more in detail in some other better ways to measure percent weight volume, other than percent weight volume, so like molarity and stuff, and even other percentage based things. Like I'm not just like poo-pooing percentages altogether. Like you can use percent weight, percent volume. Those can come in handy, and those at least you're dividing between things with the same units. So like I just don't get how you can do grams per milliliter and call that a percent. But anyway, it's because it's the percent compared to like water or whatever. But yeah, so I always found this super duper confusing, and so hopefully this explanation can help people. So let's go back to cookies for a minute. So, and let's introduce more formally this concept of molarity. So a mole is Avogadro's number, and it's kind of like a biochemist dozen, except that it means 6 times 10 to the 23rd of something. So it's this really, really big number with lots and lots of zeros. And this lets us talk about large quantities of things. And even sometimes though, because they're large quantities, but they're large quantities of really, really tiny things, so they come in really handy because we're not just talking about like single molecules floating around. We're talking about lots and lots of molecules floating around. So molarity comes in really handy because it's a measure of concentration that tells us how many like of those molecules are floating around per liter of a solution. So it's kind of telling us like the likelihood that we're going to bump into one of those things. I mean, it's not a probability in any way, but it's telling you like the concentration in a way that kind of gives you a sense of like how crowded in that thing is the solution. And so we use molarity. We can do this for like anything. So if we were making cookies, we could have like, if we had 50 chocolate chips per cup, it would turn out to be this like really, really small number molarity of chocolate chips. We do the same thing with almonds. So basically we do this with molecules more commonly. And although we have a lot of molecules in a solution, so sometimes we make really concentrated solutions where we have like 5 molar NaCl solution or something. We're making a stock solution, which is something that's kind of really handy, so you can dilute it. So you have it like pre-dissolved, and then you can dilute it to what you want. But a lot of the times we're working with like milli, micro, nano, picomolar. So we can just stick these prefixes in front of molarity. It's kind of like you have like centimeter, milliliter. It's the same idea, except here we're doing millimolar and that sort of thing. And so this is basically how we usually report concentrations in biochemistry. But what about that whole like percent weight volume thing? So that would mean that it would be grams of chocolate chips or almonds or whatever per 100 milliliters of batter. So if we have 1 gram of chocolate chips per 100 milliliters of batter, that would be a 1% weight volume chocolate chip solution. But since batter is denser than water, this wouldn't work well. And it never really works well anyway. Sorry, I really don't like percent weight volume, if you hadn't noticed. Okay, but where does one place that you might see it, let's look at an example of where you might see it, is in medicine with saline. Normal saline is reported as 0.9% weight volume. So this means that you have 0.9 grams of NaCl per 100 milliliters of solution. So remember, water at room temperature has a density of 1 gram per mil. And so if you don't have that much salt in there, it's not going to change much of the water's density. So we can say that the density of water-based aqueous solutions like normal saline is still about a gram per. That whole gram in a milliliter came from salt, would be 100% solution. But so a gram per 100 milliliters is a 1% solution. So weight volume percent is like not a real concentration. It's not a real percent, but it sometimes works out. And so let's look at why this is for this normal saline. But to do this, we need to first look at the idea of formula weights and molecular weights. And then we'll come back and see how we can use that information to see why this like little like shortcut can work out for dilute aqueous solutions. So sometimes it'll be called a molecular weight and sometimes it'll be a formula weight. And so this is because, so basically both of these are going to tell you how many grams 1 mole of that formula unit weighs. So by the formula unit, so this is sucrose, so like table sugar. So it has this formula. So this is basically telling you all of the atoms inside of it. And so, but here you'll see that it's like a molecular weight, so MW. What if you go to sodium chloride? So here you have NaCl. Here it's shown as a formula weight. Sometimes it'll just be like based on the brand or whatever, but technically this is right. Like I mean, like a formula weight would be correct for the other two because it's like the same, whatever. But we're using formula weight here because it's an electrolyte. And what that means is that when you dissolve sodium chloride in water, the sodium and chloride are actually going to dissociate. They're going to come apart. So when you have a solution, basically that means that each formula unit, or not each formula unit, each molecule is going to get a full coat of water. That does not mean that each formula unit is going to get a full coat of water. So what do I mean by this? Imagine you had like a Kit Kat and you had a Rolo bar. So each Kit Kat bar has 4 pieces, but when you stick it into like when you unwrap it, they stay together. But when you unwrap that Rolo bar, those things come apart. And that's kind of the idea with an electrolyte. So basically, when you put in your sugar, even though it's made up of glucose and fructose, those aren't coming apart because those are held by covalent bonds, which are strong. But when you have sodium chloride, these are just held together by ionic bonds, which are more like really strong charge-based attractions. So when you put it in water, they'll actually dissolve and dissociate. So now you have Na plus Cl. But because you're giving this formula weight, so you're saying this is how much a mole of NaCl weighs. So this means that it's taking into account both. So when you dissolve it, you'll have a mole of sodium and a mole of chlorine, and their ions, they'll be separated, but you still have a mole of each if you calculate based on this formula weight. So that's where we get this like idea of formula weight and molecular weight from. So when you dissolve, you aren't breaking the covalent bonds, you're just giving each copy a full water coat. With dissociation, these come apart, the ionic bonds come apart, and then each of the ions, so the charged particles, get a full water coat. Okay, so that's where that comes from. We can find the percent weight of normal saline, which is at least better because now you're comparing the equal amounts of things. So we take NaCl has a formula weight of 58.44 grams per mole. So this is telling you that 1 gram of NaCl or 1 mole of NaCl is going to weigh 58.44 grams. And so if we had a 100 milliliter solution, we'd have 100 grams of water. But we have if we add the weight of the NaCl, now we have 100.9 grams of water, or 100.9 grams total. And how much of that weight is coming from NaCl? We end up with about 0.89% NaCl. And so you can see this is where the whole you can kind of rough estimate it's about 0.9%. And of course, too, this isn't taking into account whether the NaCl was actually going to increase the volume at all. And so we're not going to worry about that. This is just a basic idea. So what if we wanted to find its molarity? And so molarity, moles is something per liter, remember? And so if we do this unit conversion, or dimensional analysis, so I have a post on that. But basically we can use that information and align it in such a way that our units are going to cancel out. And we end up finding that we have 0.015 mole of NaCl, which is the same as 15 millimole. But for the purposes of molarity, it's moles per liter. And how many liters? We have 100 milliliters, which is 0.1 liter. And so our molarity is about 0.15 molar NaCl in the 0.9% normal saline solution. Concentration forms you might see. So mole fraction. So that's like how many moles compared to like the total amount of moles. So like how much is one thing compared to like everything. So if you had 10 M&Ms and 5 of them were red M&Ms or whatever, it would give you that sort of idea. Another one is percent volume. So this comes up in like alcohol sales with like proof. So the whole like definition of proof, I think it like changes from country to country, but for like in the United States, like 100 proof would mean like 50% alcohol by volume percentage, I think. And another form you might see is molality, which is moles per your solute per kilogram of solvent. And so this is helpful because molarity is going to change with your temperature because the volume of water is going to change with the temperature. So like the same amount of molecules are going to occupy more space at a hotter temperature because they're going to have more energy to like spread out more and resist the pull of others as much. But with molality, that's going to stay constant. Your weight's not going to change. So molality is sometimes used as well.